Welcome back to physics. We're discussing acceleration in this chapter. Let's begin by going over last night's homework.
A bus that is traveling at 30 kilometers per hour speeds up at a constant rate of 3.5 meters per second squared. What velocity does it reach 6.5 seconds later? So I'm going to use the formula final velocity is equal to my initial velocity plus acceleration times time. In this particular case, my initial velocity I'm going to keep in kilometers per hour. My acceleration is 3.5 meters per second squared, and it's going on for 6.8 seconds. Now, I do need to convert either the kilometers per hour into meters per second or the meters per second into kilometers per hour. Well, since typically we are in a bus and we're normally going to have our rate in kilometers per hour for something like that, I'm going to go ahead and convert the meters per second. So 1 kilometer, there are 1,000 meters, and then there are 3,600 seconds in an hour. Now, with Sig Figs, I've got 2 in my originals over here, so I really only have 2 here. Remember that these are exact values. They are not going to affect Sig Figs at all. So I have 2 still here. I'm then going with addition properties, so I go by place value. This one's exact out to the tenths. This one is exact out to the units. So I need to round to the units, giving me 115 kilometers per hour. If a car accelerates from rest at a constant 5.5 meters per second squared, how long will it take for the car to reach a velocity of 28 meters per second? So again, I'm using the final velocity is equal to initial velocity plus acceleration times time. My final velocity I want to be 28 meters per second. My initial velocity is 0 because it says it's starting from rest. My acceleration is 5.5 meters per second squared, and I want to know the amount of time. So if I divide 28 by the 5.5, I get 5.090909 seconds. As I look, I've got 2 Sig Figs here and 2 Sig Figs here. I'm doing division, so I'm going to be left with 2 significant digits, which would be 5.1 seconds. And then number 21. A car slows from 22 meters per second to 3 meters per second at a constant rate of 2.1 meters per second squared. How many seconds are required before the car is traveling at the 3.0 meters per second? So once again, final velocity is equal to initial velocity plus acceleration times time. My final velocity I want to be 3.0 meters per second. My initial velocity is 22 meters per second. My acceleration is going to be a negative 2.1 meters per second squared. It is negative because it is slowing down, which means it's going in the opposite direction as what I've defined as positive. And we are looking for the time. So if I subtract 22 meters per second from both sides, it gives me negative 19 meters per second. And in this particular case, I was doing subtraction. I subtracted this from this, so I got to follow the subtraction rules. This one is exact out to the units, whereas this one's out to the tenths, so I need to be exact out to the units. So negative 19 meters per second is equal to negative 2.1 meters per second squared times the time. So if I divide the negative 19 by the negative 2.1, I get the time being 9.0476. I've got 2 Sig Figs in each of the numbers that I'm dividing, so 9.0 seconds is the answer.
All right, so in yesterday, we learned about the position with constant acceleration, and we used graphs to show the total displacement. Up on your screen is the last slide that we covered yesterday, and you can see how we've derived that final formula there at the bottom of the screen. That final distance is equal to initial distance plus initial velocity times time plus 1/2 the acceleration times the time. Now, in some cases, it is more beneficial for us not to have the time in there. So is there a way to get rid of time? In this particular equation, yes, there is. So if we look at the equation that we've used several times on our homework, our final velocity is equal to initial velocity plus acceleration times time. If we take that equation and we solve for time, and then substitute that value for time into this equation, we come up with a new equation. It is the final velocity squared is equal to an initial velocity squared plus 2 times the acceleration times the change in distance. I did not show all the workings of how it was derived. I just kind of explained it because, quite frankly, it looks a little confusing when you see it all written out. But it does end up being that equation. So let's use this equation and solve a problem from example 4. An automobile starts at rest and speeds up at 3.5 meters per second squared after a traffic light turns green. How far will it have gone when it is traveling at 25 meters per second? I'm going to state that my initial distance is 0. My initial velocity is 0 because he's starting at rest. My final velocity is going to be 25, and my acceleration is 3.5 meters per second squared. And I want to know the final distance. So if I take my final velocity squared is equal to initial velocity squared plus 2AD, and I substitute in, we can rearrange the formula first, or we can substitute in. I find that most students would prefer to substitute in the values and then work it out. When you do that, you get 89 meters. So in that time that it took him to accelerate to 25 meters per second, he traveled a total distance of 89 meters.
Here we have a skateboarder moving at a constant velocity of 1.75 meters per second when she starts up an incline that causes her to slow down with a constant acceleration of negative 0.20 meters per second squared. How much time passes from when she begins to slow down until she begins to move back down the incline? This one here, I'm probably going to use my final velocity is equal to initial velocity plus acceleration times time. My final velocity I'm going to set at 0 because she's moving up and she's slowing down, and I want to find out how long it takes until she begins to move back down the incline. So she's going up. At some point she's going to have to stop in order to start moving back down. So that point at which she stops, her velocity is going to be 0. That is the point that I want to know. Her initial velocity is 1.75 plus the acceleration of negative 0.2, and then our time, which we don't know. So if I subtract the 1.75 from both sides, that is equal to negative 0.20 meters per second squared times the time. So if I divide both sides by the negative 0.2, it gives me a time of 8.75 seconds. Now, with significant digits, here I have 3, I still have 3 over here, I only have 2 here. The first 0 does not count, so I'm limited to 2 Sig Figs, which gives me a final answer of 8.8 seconds. All right, let's try number 27. A race car travels on a racetrack at 44 meters per second and slows at a constant rate to a velocity of 22 meters per second over 11 seconds. How far does it move during this time? My initial velocity is 44. My final velocity is 22. My time is 11 seconds. I want to find out what the distance is. And I do know that my acceleration is constant. So what I encourage you to do is write down the things that you know, and then you can look through your formula list to see which of the formulas is going to be most useful in this situation. So my acceleration, I'm going to have to figure out. Acceleration is the change in velocity, which is 22 minus 44 meters per second, over time, 11 seconds. So my acceleration is a negative 2 meters per second squared. And now I can solve for my distance. I'm going to use my final distance is equal to my initial distance, which we'll just call 0, plus the initial velocity of 44 times the time, which is 11 seconds, plus 1/2 my acceleration, which is a negative 2 meters per second squared, times the time of 11 seconds squared. So I have 484 meters. When I multiply that out, this gives me a negative 121 meters. So that gives me a total of 363 meters. Now I want to check my Sig Figs to make sure I'm still good. I've got 2 here and 2 here, which means I need 2. Over here I've got, would originally be 2 and 2, so I need 2 here. So my final answer should be 360 meters.
All right, that brings us to example number 5. You are driving a car traveling at a constant velocity of 25 meters per second when you see a child suddenly run onto the road. Rather than hitting the accelerator, you hit the brake. It takes you 0.45 seconds for you to react and apply those brakes. As a result, the car slows with a steady acceleration of 8.5 meters per second squared and comes to a stop. What is the total distance that the car moves before it stops? So once again, I'm going to write down everything that I know. I know my initial velocity is 25 meters per second. I have a delay of 0.45 seconds. My acceleration is going to be a negative 8.5. And my final velocity is going to be that of 0. So what I'm going to do first, I'm going to figure out how long did it take for me to react? How far did I go before I was able to start hitting the brakes? So I take my speed of 25 meters per second and I multiply by my reaction time of 0.45 seconds. That gives me 11 meters. So the car traveled 11 meters in the time it took me to hit the brakes. Now, once I've started hitting the brakes, now I can use my final velocity squared is equal to initial velocity squared plus 2AD. Once again, if I substitute in the numbers and then work it, or if you rework it and then substitute in numbers, you should get an answer of 37 meters. So my car traveled 11 meters before I hit the brakes, and then it traveled another 37 meters once I started hitting the brakes before it came to a stop, which means I traveled a total of 48 meters.
Number 30. A man runs at a velocity of 4.5 meters per second for 15 minutes. When going up an increasingly steep hill, he slows down at a constant rate of 0.05 meters per second squared for 90 seconds and comes to a stop. How far did he run? Alright, so I've written down everything that I know. I did change time into seconds since everything else is in meters per second. So first of all, I'm going to figure out how far did he run before he hit that hill and started to slow down. So he was traveling at 4.5 meters per second, and he did that for 900 seconds. So his initial distance, I'm going to call 4,050 meters. Technically, I've only got 2 Sig Figs, so we'll keep that in mind. It slows down at a constant rate of 1/2 meter per second for 90 seconds and comes to a stop. How far did he run? So I'm going to call this D2. That is equal to D1, which we'll just leave as the 40/50. My initial velocity times time. The initial velocity that he was running was 4.5 meters per second times the time. In this case, the time is going to be 90 seconds plus 1/2 the acceleration, which is negative 0.05 meters per second squared, times the time squared, which again is the 90 seconds. Alright, so his second distance is 202.5 meters. Again, I'm going to be limited to 2 Sig Figs here. Technically, I've only got 1 here. So I need to round to the hundreds, which is here when I do my subtraction. And then when I add those two values together, again, I'm going to have to round to the nearest hundred. And so that gives me 4,252.5 meters, with Sig Figs be 4,300 meters. Rebecca is training for an upcoming 5K race. She starts out her training run by moving at a constant pace of 4.3 meters per second for 19 minutes. Then she accelerates at a constant rate until she crosses the finish line 19.4 seconds later. What is her acceleration during the last portion of her training run? The total distance that she needs to travel is going to be 5,000 meters. During the first portion of her run, the first 19 minutes, or 1,140 seconds, she is traveling at a rate of 4.3. So what I'm going to do first is I'm going to try to determine how far did she run during that first 19 minutes. So if I take her time of 1140 and I multiply by her speed, that gives me a total distance of 4,902 meters. So that means her distance to finish the race is going to be the other 98 meters. She accelerates at a constant rate until she crosses the finish line 98 meters away, and she does that in 19.4 seconds. What is her acceleration during the last portion of the training run? So I'm going to use the final distance of 98 meters is equal to the initial distance, which we'll just leave at 0, plus my initial velocity, which we know is 4.3 meters per second, times the time, which is 19.4 seconds, plus 1/2 the acceleration, which we don't know, times the time squared, which is the 19.4 seconds. Alright, so when I multiply out, I'm going to go ahead and subtract the 83.42 from the 98. It gives me 14.58 meters is equal to 188.18 seconds squared times A. So if I take that amount and I divide by 188.18, I get an acceleration of 0.077479, and that'd be meters per second squared. Now for my Sig Figs. I've got 2 here, which means I only really have 2 here when I do my subtraction. Over here I have 3, so when I do my division I'm going to be left with 2. That gives me a total of 0.077 meters per second squared.